Is it good?
Yeah.
I think it should be recording. So we can start. Hi, everybody. Welcome to another session of our Neuro-Symbolic interest group meeting as part of the Alan Turing Institute. And we're really excited to have Tarek and Christoph giving a talk today. There was another talk last week. In case you missed it, we upload our videos on YouTube. And the general format is 45 minutes of the talk and 15 minutes of questions. And you can drop your questions in the chat window during the talk as well, but we might as well wait to the end of the talk before answering the questions. So both Tarek and Christoph, from the title of the talk, work on Neuro-Symbolic AI. In fact, Tarek has been quite instrumental in running some of the community events around Neuro-Symbolic AI. If I'm not mistaken, he's one of the co-founding members of the Neuro-Symbolic AI journal. Is that right, Tarek?
Yes.
But he's had a long history working on various aspects of logic programming, explainability, inductive logic programming, Neuro-Symbolic AI, with some very interesting work looking at both from a concept invention strategy, but also looking at creativity, which is what this current talk is going to be. And Christoph is his collaborator at Sony AI, who I believe has also been working quite a bit on explainability and semantics and Neuro-Symbolic AI. So without much ado, I welcome them, and please take it away, Tarek and Christoph.
Thank you. First and foremost, thanks for having us. We're super happy to be here and have the opportunity to tell us a bit about the work we've been doing at Sony AI around AI for scientific discovery. Let me share my slides. First of all, as we are in terms of AI research units, rather the younger kids on the block compared to some of our bigger siblings from other big tech companies, who is Sony AI? Sony AI, we are Sony's dedicated long-term frontier AI research unit. And we always focus on imagination and creativity. So Sony as a company defines itself as developing tools empowering creators. And we are the AI building block in that push. I'll tell you a little later how that squares with AI for scientific discovery. But before that, there is a strong commitment on our side towards three core values or key stances. One is diversity. You can also see that in the setup of Sony AI. One is transparency, and one is social good. The way Sony AI operates is we are clustered into flagships. So flagships for us are big projects, multi-year, significant investment, and they always aim to push the scientific frontier forwards, whilst at the same time resulting in outcomes that empower creators. You can see the headlines here. For more details, have a look at our website, ai.sony. We, so Christoph and I, are part of the scientific discovery flagship. And whilst you might expect Sony to be active in games, in music, in movies, yes, Sony also is active around scientific discovery precisely because Sony believes that science and the scientific activity is a very creative endeavor. And our mission statement for my group is that, hey, help scientists be even more creative, empower them to push boundaries which have held up science or slowed down science for a long time. As an organization, we have over 200 members, researchers, scientists, engineers, operations support. We have physical offices in Barcelona, which is where Christoph and I are assigned, Bangalore, Boston, Tokyo, and Zurich. But we also operate remote teams in other European and Northern American countries. Okay, and now let's jump into the actual content of our talk. As the title already promised, we want to have a look at the creative part of scientific discovery. And before anyone feels that I am cherry-picking what part of science is creative, of course, science throughout the entire scientific process is a process of creativity. Still, we focus on one particular step, namely hypothesis generation. So the very early ideation of what, as a scientist, do I want to research, and what is my assumption which I want to prove or falsify in the scientific process. In this talk, we'll have a look at a recent model of ours called THIGER, which basically is a temporal graph-based approach to generating novel hypotheses from published literature encoded in knowledge graphs. Christoph then will show a particular piece of THIGER, namely a novel approach to transforming knowledge graph embeddings into better interpretable structures. And explainability and interpretability are a key element in any AI for science endeavor. We'll come to that a little later. But before getting into it, maybe not everyone is familiar with AI for scientific discovery as a field. I'm sure everyone by now has heard of it because there's a lot of activity, also a lot of funding going into it. Still, I want to have a quick look at how we conceive of it, and I want to have a quick look why I think that us as a neurosymbolic community, we are key enablers for that endeavor to actually work and be successful. So AI for scientific discovery, I'm here quoting from a website of the European Commission. What is it? Well, the European Commission, and I think rightly so, says AI's growing role in science spans various fields. It acts as a catalyst for scientific breakthroughs and a key instrument in the scientific process. This heralds a new era of accelerated results. It pushes scientific frontiers and produces outcomes beyond the reach of current tools. Okay, so it's about providing key instruments to the scientific process, catalyzing further scientific breakthroughs, and accelerating results. Why would one want to do that? It's always a good question to ask why we're actually doing something, even if we know we're able to do it. Well, in a lot of AI for science, you currently see that people are indeed trying to use it to address some of the pressing societal challenges we are facing, be it climate change, be it applications to health, be it applications to the green and the digital transition. So in a way, what is currently, and I can only encourage you all to join the AI for Science push, what is very positive about it is that, yes, it's a novel field, it's exciting to explore it, but also there is a very high likelihood that your explorations actually will contribute to bettering the human condition, which hands down at the end of the day is the purpose of all science. If you have a look at how AI comes into play in the scientific process, there is 3 places. Taking it from left to right. So if you think about how do scientists go about it, particularly in the life and the physical sciences, maybe a little less in the structure sciences, how do scientists go about coming up with a new result, a new breakthrough? Well, first, you have a look at what is my hypothesis. In order to do that, you probably build on past research, and then you come up with an assumed connection between entities in your domain of research, this assumed connection being the hypothesis. Then you go into, okay, how do I validate that hypothesis? You design experiments. Once experimental design has been done, nowadays there's 2 ways forward, and they might just be successive steps. You can either go for in silico experiments, so computationally validating your hypothesis, or at least computationally stress testing it, before you then move into wet lab experiments, so experiments where you actually in a lab test what's going on. Correspondingly, here the 3 places where we possibly can help: hypothesis generation being the first one, in silico experimentation the second one, and then lab automation the third one. Let's have a look at them in turn, what that might mean. So lab automation, there we are very much thinking about integration of self-governing tools and workflows into the laboratory. That can go from robotic support, automated centrifuges, robot arms opening or closing items, up to the level where you actually have closed lab environments, which are self-monitoring and self-experiment steering. So there's a few demos around where people, for instance, have full cycle closed mini labs where they can grow certain yeast cultures. You then have sensors for humidity, for the light the yeast experiences. And then depending on what growth you detect, you vary the environmental conditions. And thus you, in a way, auto-experiment the full cycle. In silico experiments, I already mentioned, that probably is the place we all know or have heard about most, thanks to, for instance, AlphaFold, but thanks to also breakthroughs from researchers at IBM and NVIDIA around experimentation in materials science. in silico, actually, studies and experiments conducted via computer simulations or via computational modeling. So there is a wide range of applications. Probably what's best known are the first two ones on my list, so either drug discovery and development or genomics and bioinformatics. So you, having the Alan Turing Institute in the UK, presumably are familiar, for instance, with isomorphic labs, the Google DeepMind spin-out, who are rather heavily researching into drug discovery. Still, as I said, there's also chemical synthesis and material science. There is also then epidemiology and public health. All of these things, scientific hypotheses can be stress tested, maybe not fully validated, but definitely stress tested using simulations rather than really going through a lab test. Here, if you're rewatching the presentation later and you want to have a look at, okay, so what are some of the companies active there in some of the areas, we just pulled this from CV Insights. You can see definitely for drug development, there's a lot going on. Feel free to follow up. And then finally, hypothesis generation. You see, we now made it all the way from the final stage, the lab, through the virtual experimentation to the stage where we generate hypotheses. So where we enable scientists to come up with novel assumptions about the world or relationships within the world, which they can then test. Here, the idea is that by deploying AI, we can enable scientists to actually access a hypothesis space that otherwise would have been locked to them. Why? For instance, because human working memory is limited. For instance, because as an individual scientist, you can only read so many articles, you can only catch up on so many new discoveries. All of this, so the assumption goes, and we very much subscribe to that assumption, can be boosted if you combine humans and AI support tools in the proper way. And as you can see on the visualization, so we think that humans plus AI can access a part of the hypothesis space that otherwise would have been inaccessible. It's important to keep in mind, you probably still can't access all possible hypotheses that are out there. Still, that's a point that more goes into the philosophy of science side nonetheless. I think it's worth making. So I promised that I would present an argument why we as a neurosymbolic community are actually very likely to be pivotal in making this happen. So let's go through the stages again. If you look at lab automation, what that very, very often means is real-world human-robot collaboration scenarios. So you have a lab, you automate certain activities. Still, there is humans interacting either for things which currently you can't automate yet, or for things which require more flexibility than your program system can provide. What that means is that you are almost always dealing with complex planning domains and with frequent replanning due to changes in the environment. Robot planning classically is very much symbolic, and it works well for limited domains, controlled environments. We all know it doesn't work just as well if you go into either very complex or very dynamic domains. Still, as of recent, so the last few years, there's a growing number of neurosymbolic robot action planning proposals coming forward, and they look really promising. So this is also one line where instead of exclusively looking at interactions in warehouses, exclusively looking at autonomous transportation modes, I think it would be very valuable if researchers, maybe some of us here in this call, would also start to consider, hey, can we help in labs? Can we accelerate the scientific process like that? Then in silico experimentation, what you're looking at there very often, protein folding, molecule generation, material prediction, is actually using some form and shape of generative model. I'm very loosely using the term generative model here. I don't want to have it tied exclusively to LLMs. Some form of generative model predicting a physical phenomenon. Challenge there is you always have a large combinatorial search space. So proteins can be folded in many ways. Molecules can be combined in many ways. So what is the case is that all of these domains have governing laws. easily called the laws of nature. So molecules don't combine arbitrarily. Proteins don't fold in a random way. And additionally, very often you have starting hypotheses. So you don't have to brute force the entire search space, but you can have, starting from previous research, have a pretty good guess what form and shape the solution you're looking for might have. Again, that actually, in my opinion, very much asks for neurosymbolic people looking at generative models which combine statistical search with structured information regarding the search space, either regarding where to start or shortcutting some of the exploration because you know what's the structure governing the space. And then finally, very similar but very different, hypothesis generation. There, what you're trying to do is you're trying to formulate specific relationships between entities in a specific domain of science. You have previous research results as input, and you have very often observations and data as input. It's not quite the in silico experimentation setting, because here you actually are, you might not yet know which governing laws apply. You're more hypothesizing which ought to apply. Still, again, we're looking at a task that loosely can be described as relationship prediction over structured knowledge, namely the past scientific research, which you want and have to enrich with quantitative information, either in order to sharpen your hypothesis, also because the quants, the numbers, might be a core part of your hypothesis. Think about applications in chemistry and material science. It's no good to say, hey, this catalyzes that. In order to really contribute to the research process, you probably have to say quantity X of this catalyzes quantity Y of that. So, and why do I think that even if you now say, no, I can solve all of this without neurosymbolic shenanigans, why do I think that it has to be neurosymbolic as of now? Well, have a look at what we consider science. And I'm here quoting from the Oxford Companion to the History of Modern Science. Modern science is a discovery as well as an invention. It was a discovery that nature generally acts regularly enough to be described by laws and even by mathematics, and required invention to devise the techniques, abstractions, apparatus, and organization for exhibiting the regularities and securing their law-like descriptions. As long as we say that science is about insights and not only about case-by-case predictions, we have to be able to make the step from these are the numbers, these are the individual case descriptions, to here is the governing laws. I know that by now many people have different understandings of what is included and what is the core mission of neurosymbolic AI. To me, this ability to go from a distributed representation to the governing rule is half of the very core of neurosymbolic integration, namely generalization, the step from correlational, data-based, distributed information to the governing laws it has. And science exactly does that, at least until now. There is a debate whether it will do so in the future, depending on how successful we are with the AI part and what type of AIs we deploy. But at least until now, science goes from individual observations to laws. Okay, so enough of the initial words. Let's have a look at what my team and I at Sony AI actually are doing. We are trying to tackle the hypothesis generation problem step by step. Of course, hypothesis generation is a mouthful. So it's a huge theme, and we are, of course, only addressing parts of it. But the two pressing issues we found when talking to researchers in the life and physical sciences is, on the one hand, they say that they can't keep up with the sheer volume of publications. I've here pulled two numbers. So 1980, there was at around 500,000 of scientific publications newly appearing. 2020, we were at 2.5 million. So that's 2.5 million over and on top of what had been published in the history of humanity up until 2019. Also, what you see is that scientific phenomena, or at least the phenomena which are being studied, are becoming more complex. For instance, here, taking biomedical as an example, aspirin is made up of 21 atoms. Herceptin, which is a cancer drug, is made up of at around 25,000 atoms. So on the one hand, there is a lot of information being published every year. It's too much. People actually use the word avalanche when talking about it. On the other hand, the information that's being published is more complex than it used to be in the past, both of which pushes human limitations. You can't read all the papers, and a lot of the papers may be pushing your cognitive limits in terms of complexity. What we are trying to do is something actually quite traditional. So we are trying to infer new knowledge from literature by connecting fragments of information over time. The vision we are having with that is we want to have scientific discovery. So hakken is the Japanese word for a scientific discovery. We want to build prediction tools which use literature in order to predict scientific research breakthroughs, basically helping scientists with providing them with new hypotheses, new assumptions they then can test, which our model knows are likely to be true. Still, the important part here is we generate hypotheses, so we generate assumed connections between domain entities in a science domain, judging whether they are relevant, developing the experimental designs, seeing through all of that is currently left to the human. And we think it's quite okay that it's left to the human, because the machines, at least the ones we are building and the ones we've seen, are really good at solving the thing on the left. Humans are really good at solving the rest. So quick nod to the people on whose shoulders we are standing. Literature-based discovery is the keyword. And this actually started already in the 1980s, originally in the library sciences, curiously, with the work of people like Altschuler and others. So our recent publication in the AI review, you can see the link to the open access article here, introduces something we call THIGER. And THIGER is a hierarchical encoder model which captures temporal information in a knowledge graph while simultaneously updating node embeddings on the task. So let's take a step back and I'll jump to the result. Apologies for that. The question we are trying to address, rephrasing, or actually rather making more precise what I said on the previous slide, is given a knowledge graph with scientific information. So running example in this deck actually will be nutrient and health information. Certain foodstuffs contain certain nutrients. Certain nutrients have certain beneficial or detrimental health impact. We take this from the corresponding literature, build a knowledge graph, connecting entities as nodes with other entities if somewhere in the literature a connection between the foodstuff and the health information has been established. Can we then take this graph and predict further missing connection between some of the nodes? And each of these missing connections, if it truly is missing, so if it's not a non-existent connection, but if it's a missing connection, so a connection that should be there but has not yet been discovered, is a new hypothesis. How do we do that? Well, you could now take a static knowledge graph and train on it and then try to predict additional connections simply by the structure of the graph and the elements in it. What we decided to do, because we thought and we believe we are right, that it adds significant additional information, is we do not take one static knowledge graph, but we actually take a sequence of graphs. So we actually say, hey, here is the, for instance, food health knowledge graph as you could build it from the literature in 1970. Here's the knowledge graph as you could build it in 1980. Here is the knowledge graph as you could build it in 1990. In a way, the preceding knowledge graphs are always the core of the following ones. Sure, there is a couple of paper retractions, but for the sake of the argument, let's ignore that for a moment. So you do get a sequence of growing and more tightly interconnected graphs. And we believe that the growth and the additional interconnection, the dynamics of those, provide crucial information which help to better and more reliably predict missing links. Giving you the visualization, so this is a very simple example around connections between type 2 diabetes, insulin, the pancreas, GLP-1 agonists, and Parkinson's disease. At some point in time, people had realized that diabetes, insulin, the pancreas, and the GLP-1 agonists have some connection. Then researchers found, wait, Parkinson's disease and insulin have an additional connection, and the GLP-1 agonist and insulin have a direct additional connection. And yes, it's a connection mediated by the pancreas, by the way, no surprise there. And then someone figured, hey, the GLP-1 agonists actually are partially impacting on type 2 diabetes. So there's yet another edge. What we now do is we take this sequence, and we then, for instance, could get as a prediction from our model, hey, GLP-1 agonists also have a direct connection to Parkinson's disease. Before we now presented our new approach, there has been people looking into using these temporal dynamics, including actually one of our team members. The previous, most recent approach was to use recurrent neural networks. And you would then embed the sequence of graphs one by one. Downside of this was that, not surprisingly, over longer time intervals, so over longer sequences, you would have problems with information loss. It just wouldn't work as well for long distance connections. The approach we are taking instead is a hierarchical transformer. So as you can see here, we pairwise embed into the attention layer until we get to now, and then this is combined in a final link prediction score. I'm going through this really fast, I know. I want to point you to the paper for the details. It's quite extensive write-up. You can find the algorithms and everything there, but I personally think it's better if we have a look at the intuition behind it and then can clarify things in the Q&A or in the paper. The architecture in which you then end up is something like this. So the hierarchical graph transformer takes as input the aggregated node pair embeddings obtained at each time step tau. These temporal node pair embeddings are then encoded, and you keep encoding upwards through a sort of pyramid until eventually the final output is the generalized node pair embedding across all the steps. We trained that model. It's actually fairly trainable, at least on the data set we used. I'll tell you in the evaluation section what data sets we used, but it's a data set with at around 5,000, at around 5 million node pairs. Or if you want, it's actually triplets, because you always have entity, and the publication timestamp is temporal information. It turned out that this model can indeed capture and utilize the temporal information in the data to learn a better hypothesis generation model. It's way more flexible to long time windows than the previous recurrent neural network architectures, and it's quite robust to different temporal data configurations. Still, if you're doing this naively, so if you really just take what you find in the sequence of knowledge graphs, there's a couple of issues with using this type of data and that type of model. Namely, these knowledge graphs, although scientists producing a lot of results, are actually really sparse. So there is a huge number of edges in the graph which ought to be there because two entities have a connection, but which have just not been mentioned in the scientific literature, either because they were considered too trivial or because they haven't been discovered yet. If you now need negative samples, you could, of course, say, well, whatever I do not have as an edge in my knowledge graph, I take as a negative sample. But there, what I just said strikes, because you can't be sure that if a edge isn't there, it really isn't supposed to be there. You, in a way, have conflated the true negatives and they're not, as of yet, not discovered ones, so your prediction target. And the positive data, the edges which are there, are potentially noisy. Retractions, also things where someone was a bit sloppy in the write-up, things where the graph extraction from the original scientific texts doesn't work well. Yeah. What we then did is we used fairly classical ideas, but adapted to our use case, from active curriculum learning to choose highly informative and high utility subsets of the negative and positive sample. So the negative pair sampling we're doing with an active learner. We try to use negative pairs which are informative, representative, and diverse. So informativeness, there we're using an entropy-based metric to model the prior knowledge we have. Representative, we use a core set of edges with which we hope to cover the entire embedding space. And we try to sample diverse edges, looking at the gradient space for picking them. As regards to the positive pairs, classical curriculum learning. So we try to start from easier examples and then gradually feed into more difficult ones. And there we use the model prediction uncertainty as a sort of difficulty score. So as I said, this is, in terms of paradigm, quite close to how you just do that. But the trick was adapting it to our setting. This then gets you what we call THIGER A. So THIGER with active curriculum learning. You have the discovered connections with the curriculum learner sampling positive pairs. You have the undiscovered connections through the active learner sampling negative pairs. And it turns out, building this into a complete architecture, combining all things I showed you, you get, at the end, a classifier which actually works really well. Here, the benchmark results. We are always benchmarking on two settings. So one is called transductive. Probably you know that, but just in case. There, you're utilizing data from all nodes during training. The other one, inductive. At least one node in each evaluated node pair had not been seen by the model during training. And we then evaluated on several data sets, 3 classical data sets, Wikipedia, Reddit, Last.fm. They are very often used in the literature for this type of graph link prediction. And then a biomedical data set catering to our food health setting. Standard interaction data sets. There, so in red, you have the best in category, in blue, you have the second best in category. There, our model scores relatively well, so we push a lot of the previous state-of-the-art results. And what you also see is that indeed adding the active learning or the active curriculum learning component really improves the model performance. Still, this was comparing it to a general graph link prediction setting. If we now have a look at biomedical in particular, our approach actually outperforms all of the previous model. And to be fair, for instance, logistic regression, GraphSage, and AGAPA, which probably is the most famous one, they are static models. Still, both in transductive and inductive, actually, depending on how you set certain of the loss and decision parameters, our model usually currently pushes the state-of-the-art a little higher or a lot higher, depending on the individual case. Still, the real test, and then I'm actually through with my part of the talk, and I'll hand over to Christoph. The real test was we just got ourselves biomedical experts. And we sent them 400 of the hypotheses we had about food and health. And they found that 70% of the hypotheses we generated actually were supported by the literature, meaning we hadn't trained up to 2024. We actually had trained up to 2020, if I remember right. And 70% of the hypotheses had been proven true since then. For the other 30%, the expert judgment was that, yeah, a lot of this looks right. And for some of the most prominent ones, we actually found that there currently are studies ongoing. So we also take that as validation, not yet that they are true, but that at least independent experts consider them likely. As an example, here is 2 of the hypotheses that were generated. So one suggested a connection between gingerly oil and benzoxazinoid. Here you get, for convenience, the connecting knowledge graph around it. The other one would suggest a connection between soybean oil and senile osteoporosis. I have to say, unfortunately, this, if you then have a look, is a negative connection. So if you have osteoporosis, you might want to stay away from soybean oil because phytic acid apparently hinders calcium absorption. Still, it's this type of connection we're predicting. What are our next steps in general? Well, what I've shown you now is a link predictor. So it predicts that 2 entities in the domain likely have a relationship. We are now trying to also predict the type of relationship. So we're trying to add edge classification over the predicted links. It shouldn't only tell you, hey, soybean oil has a relationship to senile osteoporosis, but it should tell you soybean oil is detrimental for senile osteoporosis, for instance. Then, as I said, we started with talking to researchers, and we very much try to build tools that empower researchers. For them, if the machine tells them, hey, soybeans and osteoporosis have a negative relationship, that's not enough. they need to understand where it comes from. So they need to understand, A, how the model comes up with it, but also what's the context for it. They need a mechanistic understanding of sorts, and they need a context understanding. And this is where Christoph will tell you more about, one of our directions there. Then we are scaling it on much larger data sets, and I already can tell you it's looking good. And eventually, of course, we hope to build an end-to-end system which can be used by domain experts and which domain experts want to use. The important part there, domain experts for us usually aren't computer scientists. So particularly this part about explainability and interpretability is paramount there. And on that note, Christoph, over to you.
Thank you so much, Tarek. Let me share my screen. There we go. I hope you can see the slides now.
Yes.
Awesome. My name is Christoph Wehner. Thank you so much for having me. I'm a data scientist at Sony AI Barcelona and a doctoral candidate at the Cognitive Systems Group of Professor Dr. Ute Schmid at the University of Bamberg. I'm going to present you some of our ongoing work right now, KG Explainer, which is about transforming the knowledge graph embeddings we produce into interpretable structures for our hypothesis generation work. Part of that work is Krisa Eliopoulos and Tarek. Let's jump right into it. So as Tarek was already shown to us, we are aiming to produce scientific hypotheses. We conducted user studies trying to figure out what scientific hypotheses, especially in the biomedical domain, mean to people. It turned out to be highly community dependent. However, what everyone kind of could agree on is that a scientific hypothesis is a tentative explanation about a phenomenon. Also, it should be falsifiable and so forth. If you map that to a really simple example, we see that, like, for example, a phenomenon is that SARS-CoV-2 enters the cell via the ACE2 receptor. And in order to have a full hypothesis, we need some explanation, something that tells us why we believe this could be true. Mapping that to our binary link prediction setup, we need more than just the predicted link that actually is returned by our THIGER H approach. We also need and want a subgraph that actually tells us why our model believes this link to be true. And this is what we are generating in our work in progress, KG Explainer. Everything you see here is based on the paper that is currently available on arXiv. The general intuition behind KG Explainer is that KGE models take some knowledge graph, feed them to some interaction function, and optimize the node embeddings in such a way that they satisfy the classification goal. In particular, trans-E, we can see if two nodes behave similarly within the knowledge graph, meaning that they are connected by the same relationship or similar relationship types with similar nodes. They also have a high chance to then, on an ideally trained model, end up in a similar place within our embedding space. Now, we want to figure out with our method of KG Explainer what those symbolic patterns within the knowledge graph, thus what subgraph, let the model to learn similar embeddings for nodes, triples, pairs. How do we do that? I will really have to run through this just due to time constraints. Feel free to ask questions afterwards. Feel free to reach out to me after the talk. We do that in 5 steps. The first step is that we get the k-nearest neighbor of the predicted triple in the embedding space, given all training embeddings we have. And then we return them. We then continue with those triples from which we just take the head and the tail node, subject and object, and filter them in the first step. We filter them in such a way that we only keep the pairs that are connected by the predicted relationship type within our training data. Once we have these positive pairs, so to say, pairs that are perceived similar by the KG model and are also true given the relationship type within our knowledge graph, so pairs from which our model learned its behavior, we take them and corrupt them. We also introduce local closed world assumption. It's generally called by switching out at random the head and tail node. Once we have that, we try to describe all those pair neighborhoods within the graph. We do that the following way. We iterate over each pair, and then starting at the head and tail node, we do all possible 1 to x step walks within the knowledge graph. So we start here, do a 1-step walk, do a 2-step walk, and so forth. We note them down. Then we end up with those type of triples. Once we have all those paths, we abstract them by applying a mapping to all nodes. We want all classes of those nodes, like West Europe is a region, Europe is a continent, for example. This then results into conjunctive classes we get from those abstractions. Once we have those conjunctive classes, we can go back into the subgraph neighborhood of each pair, like look how often we find a grounding for those actual pairs, and with that calculate the frequency of that grounding. How often does it appear? This then leads us to having the following tabular data frame with a bunch of instances, which are our pairs, features, which are the clauses, feature value or the frequencies, and a set membership. We know if this pair is a positive pair or a negative, a corrupted pair. Now what we like to do is figuring out which clauses are most descriptive for positive pairs while being the least descriptive for negative pairs. And this we do by fitting an interpretable surrogate model to this tabular data. We look into 3 different models for our approach: mean decrease in impurity, which we know from random forest, K-lasso, which we know from Lime, and Hilbert-Smith independence criterion lasso, which is kind of also a lasso method. Okay, once we fitted them, we can get for each feature its relevance, and we select the most relevant features. Once we have them, the most relevant features, the most relevant conjunctive clauses, we can take them, ground them in the neighborhood of the predicted triple, and end up with the actual relevant triples relevant for a model's classification. We also evaluated our approach. The evaluation we did in terms of faithfulness. What that means is we first trained a KGE model in that example here, that evaluation here, on a kinship data set, knowledge graph. We took 100 triples from our validation data where the KGE model was correct. We explained those triples and got the explanation triples. Those explanation triples we subtracted from the training set and then retrained our KGE models on this pruned training set. And measured then the performance again of the previously correctly classified triples. What we hope from this is, or hope to achieve, is that the performance deteriorates, so that would mean that we took away the reasons the model had in order to classify the triple correctly. And we compared that here in a preliminary study with a global baseline, two global baselines, and state-of-the-art comparison model, any-burl explainer based on any-burl, and we can see that we achieve quite a good performance with our method. Yeah, final remarks. We contribute here a novel post-hoc XAI method for KGE models. The method is faithful to the KGE model behavior, and we are able to create adaptive explanations, something I did not show in this presentation, but it is described in the paper. The method comes with a few limitations. The computational complexity is influenced by the node degree of our knowledge graph. We can only explain KGE methods that are based on real numbers, and extracting triple embeddings is highly based on the KGE model, so the interaction function it has, and with that also the performance may vary. Our next step, also in terms of Haken of our project at Sony AI, is taking those triples, so the reasons why a model believes some hypothesis to be true, hand them over to an LLM such that this LLM creates some nice paragraph from it to have user-friendly explanations. Yeah, thank you so much for listening.
Thanks a lot, Christoph. Thanks a lot, Tarek. Can you hear us, Tarek? Thanks a lot for your part as well. As you can see, there are a couple of questions on the chat. I'll let you get to them in a second, Tarek. Yeah, you probably had a chance to read about them. But I was wondering about two sort of philosophical or conceptual questions beforehand. It occurred to me at the start of your talk, I mean, you mentioned this idea that there is a space of the hypothesis that the humans cannot explore just because of scalability, and I agree with you. I mean, just in this, in the area of AI, we deal with 100 papers that are relevant on arXiv every day. Quite hard to catch up and stuff. But I could imagine a counter argument to that, and the counter argument would basically say that a brute force search is good for some kinds of explorations because of human memory issues and so on, but at the same time, a kind of conceptual engineering that often goes on in creativity in terms of where we harness intuition, abstraction, and other kinds of perhaps difficult to formalize or label data with. I'd argue it's not so obvious at all that computers can imitate our creativity. I mean, there's this age-old argument, I'm sure you've heard it, against strong AI, which is basically says that because we could conceptualize and come up with things like the incompleteness theorem, which are all undecidable. There is, in some sense, we're able to access some aspect of mathematical truth that is hard to formalize with the machine. What do you say about that?
So funny that you say that, because one of the things I and part of the team want to look into, and we still don't know how to really address that, would be trying to actually come up with something like a formal characterization of, given a system like the one we're building, given that the input has this and that format, is expressed in this and that logical language, and so on, as compared to what a human does, is there a type or a space or a range of hypotheses which you can characterize in one way or another, which is accessible to the one and not the other? And for instance, I believe there will be, because at least, so I'm trying to remember my classical logic classes, which are way too long gone, right? But there's different modes of reasoning humans can employ. I think that not all of these modes are necessarily represented in what our model does. If that was to be the case, it would be a reasonable assumption to say that, hey, humans should be able to access some hypotheses which your model not going to get to, and vice versa. Still, what I'm currently struggling with, and if anyone has an idea on how to do that or wants to collaborate on that, please reach out. I'm struggling with how to even tackle that, because sure, we can define a formal language and characterize the sort of inference the model does, or we can try to do that at least. But it's much harder to characterize the limits of thought on the human side.
Yeah.
But still, so my intuition is you're right. And
yeah.
one of the interesting things when you talk to biomedical researchers and you tell them, hey, we're trying to do this hypothesis generation, how would you use it? Some of them then say, hey, okay, none of them says, hey, I would just click a button and be like, send me any hypothesis. Of course, they have constraints to start with.
Yeah.
I might be working on Alzheimer's. I might be working in genomics and so on. So you actually need a querying interface, which already makes sure that your hypotheses are remotely relevant to what they're doing. Then a lot of them actually say, well, I might not need that for inspiration, but I would rather use it for hypothesis testing. So I come up with 5 ideas, I hit the button, and then I want to see whether the system also comes up with some of those. And the nice thing with the system is it might also give me an uncertainty score with it.
Nice.
So it is, as always, when you're building tools, it's super interesting to see that a lot of people use it in a different and I think smarter way than what we originally thought of. And that is partially due to us thinking about it as computer scientists, but them being domain experts. So yeah.
So, so on that note, do you see like a balance or some kind of plot you could put in where you say, you know, this much amount of human-driven knowledge and symbolic knowledge gives you this kind of scalability or learnability, but as I increase the amount of human knowledge, I see that the system scales a bit poorly or scales better. Do we have that trade-off? Do you have, you know, at least in some of the work you've done, do you have a rough sense of where this trade-off sits? Like how much symbolic input is good enough, and when should we stop?
Yeah, no, I don't, but it actually would totally be worth doing. Because you're right, at some point you probably over-constrain. Like at some point, you basically introduce your own biases and limitations.
Yeah.
Okay, there is an ERC grant there.
Good. I'll let you tackle the questions in the chat, Tarek or Christoph, whoever you prefer. I mean, if you could just summarize the question very quickly and then give your response to it, we could wrap up with that.
Yeah, okay. So Christoph, let me start from the top, and then there's 1 or 2. For instance, Christoph, I'd invite you to later reply to Lauren if you already want to have a look. And I invite you to reply to Zong Tian. I'll start on Alex, so you've got a bit of time to think. So Alex is asking, hey, there's a lot of deep learning companies and also connectionist theorists out there who say, yeah, we might not need the symbolic part. We might actually be able to get connectionist systems to do the relevant level of generalization or what have you. My response to that is that might be possible, but I believe that that would require a science sociological change. At this point, a lot of scientific rules, let's say, are actually just correlational at first until later someone phrases the general governing theory, particularly in physics. There's a lot of rules around until 20, 30 years later, someone is like, oh, wait, these are actually the mathematical governing laws. Currently, scientists and philosophers of science mostly only accept the governing laws as the final scientific end result. we might now witness an evolution of science where we say, actually, we're okay with the statistical or the correlational result. We do not need this final thing to already consider it. If that happens, that's just an evolution of science, which there were several over the last centuries, fine. As long as we say, no, we need the governing laws, I think you have to go neurosymbolic. Then there was a follow-up to that by Louis, who was asking about the AI scientist by Sakana. If you haven't seen it yet and you're interested in this, have a look. Sakana AI scientists. They actually brought out a system where they, in a very smart way, pipeline several LLMs and let them do hypothesis generation, paper writing, and review. We had a look at it, obviously, and kudos. It's really smart and it really fits their use case. Still, it has a couple of limitations around it can only deal with text at this point. They use machine learning as their application domain, and I think there's a good reason why they do it, because their experiments and their results are code. So the hypothesis is mathematical, their experiment is an algorithm, and their experiment is the test runs, and their result is an algorithm. I wonder whether that LLM approach, particularly given that LLMs still do rather poorly, for instance, at maths and so on, would generalize into other domains of actual physical sciences where there's a lot of data flying around. Nonetheless, totally worth having a look at. What you should keep in mind, though, is that computer science usually is considered a structural science, and there is quite some theorists who would tell you, no, that's not really a science. Like, you do something epistemically different in computer science than you do in physics, biomedical, material science. Then, Christoph, do you want to have a shot with Lauren?
I would prefer if you answer that one, because it's more about like THIGER, THIGER Age.
Okay, so we tried it mostly on biomedical, and there actually is two aspects to what you say there. So we tried it on different sizes of data sets. For instance, we later also tried it on a much bigger one. And you are right in that you need a certain minimum quantity of data to make this work reasonably well. What you, of course, in a way can do is you can compromise on prediction uncertainty. You can say, hey, what is good enough for you to actually assume that a hypothesis should go to testing? But you're right. Your intuition is right for doing what we're doing here, particularly if the data is messy. Like, if you, of course, very smartly select your input data, you can do with very little data, but then you're cheating. You need quantities which are non-trivial. One of the things I wanted to also mention, though, is that biomedical, or generally this food health and related domains, they are very different from chemistry and physics, because there you and us usually get away with our quantities. In genomics, it's already good if you can say, hey, this gene and that disease have a relationship. You do not have to provide 10 grams of this chemical react with 20 grams of that chemical. I actually think the problem, in order to generalize what we're doing, is less, do you get enough data? Because science is producing a lot, even in rather niche disciplines. The problem is rather, how do you then make the step out of these purely concept relationship domains, even if you can say what relationship they have, averse or catalyzing, into the domains where you have to get the quantities right. And that is then the genuine neurosymbolic step, in my mind. Christoph, I think we had Zhangtian.
I think you're muted,
yes,
Christoph.
There we go. Question is what we mean that embeddings have to be real numbers. It's actually some review we received. This issue arises from the distance function we use for our K nearest neighbor search. We use the Euclidean distance. So our embeddings have to be in a numeric space for which this Euclidean distance is defined, which are real numbers. And we are currently looking into, so considering different distance measurements and so forth to extend our reach there. However, the good thing is most knowledge graph embedding models operate in this numeric space. The next question is that on page 54, talk about 3 different explanation types. And yeah, I left them out just due to time limitations, but I actually also brought a backup slide on them. Let me show that.
I think your reviewer is right here, Christoph.
My review is right here. Oh, my awesome, I have to read the comment. Okay, the 3 different types of explanations we have here is the rule-based explanations we can provide. As I showed in the presentation, we create these conjunctive clauses, and then we continue by actually grounding them. However, we do not necessarily have to ground them. We can just provide them as some additional information. If that is useful or not, we have to like look and consider in a specific situation if this is something the user may ask for. The example I went with is the instance-based explanation. So where we continue with grounding our conjunctive clauses in the subgraph neighborhood of a predicted pair, and then we actually get the triples around it that led the model to make its prediction. The final explanation type we can produce are analogy-based explanations. In the process, we identify pairs which the model perceives as similar and for which we know that relationship type exists in our data. So something the model learned from. Now we can take the most similar pair, and thus triple, and ground our found conjunctive clauses into its subgraph neighborhood. Getting back an explanation that is basically, okay, we believe Spain is located in Europe because we know that Portugal is located in Europe. Portugal is similar to Spain. Europe obviously is similar to Europe. And for that, we also know that Portugal is located in West Europe. West Europe is located in Europe. So those are the 3 different relationship types we can generate with this method. Now, regarding the last point about generalizability. The method is not generalizable in the sense that it's not global. By selecting the k nearest neighbor, we look at a very limited space of the actual, so to say, decision surface our model learned. And thus, the explanation we find is only true for that particular instance. Okay.
Good. Thanks a lot, Christoph, and thanks a lot, Tarek, since you've gone over the time anyway. Let's close off now, but I guess the audience knows that they can reach you. But fantastic talk, very interesting, and I guess see both of you or one of you at NESI.
Looking forward. And
so
to everyone who hasn't registered yet, we still have a few tickets. So if you want to come to Barcelona, September 9 to 12, 18th International Conference in Neuro-Symbolic AI. See you there.
Bye. Thanks, guys.
Bye.